DC Motor Control by Amitabh Kumar Sinha. Constant torque motor control. See the graph. Constant power control. See the graph. Fleming's left-hand rule. Fleming's left-hand rule defines the direction of force, torque, which is applied to a current-carrying conductor placed in a magnetic field. See the picture. Placing conductor in a magnetic field. Generation of torque. When a conductor carrying electrical coil is placed in magnetic flux, it experiences force proportional to flux, current, length and number of turns of the conductor in the coil in a direction perpendicular to the plane of flux and current, as per Fleming's left-hand rule. When this force is multiplied by the torque arm, that is width of the coil, we get torque. We have force equals a constant multiplied by flux density, length of conductor and number of turns, and torque equals the constant multiplied by flux density, length, width of coils and number of turns. Basics of DC motor. Torque generation, as explained earlier, is graphically shown here. Concept of back EMF. If we apply voltage E across DC motor armature terminal, very high current may flow through it. However, due to rotation of coil in the magnetic field, a back EMF, EB, is generated to oppose applied voltage. This EMF, EB, depends upon the rate of change in flux experienced by armature coil due to rotation. In case F is maximum motor flux and N is motor speed in RPM, then EB is proportional to F multiplied by N. If RA is armature resistance, then armature voltage E is equal to EB plus IA multiplied by RA as per Ohm's law. We have EB is proportional to F, flux multiplied by N, speed or RPM. Above means N is proportional to voltage EB, divided by F flux. And motor speed is proportional to back EMF voltage, and inversely proportional to flux, and torque is proportional to flux multiplied by armature current. It is clear that we can control motor speed by controlling voltage or flux or both. Previous explanations gives us two basic equations for speed and torque control of DC motors. DC motors have two speed ratings: base speed with full rated torque and top speed with reduced torque. Equation 1, speed is proportional to voltage up to base speed and inversely proportional to flux beyond this up to top speed. Speed equals a constant multiplied by armature voltage and divided by field flux. This means speed of motor equals a constant multiplied armature voltage divided by field current. Equation 2, torque is proportional to multiplication of armature current and flux. We know that flux in a DC motor is proportional to field current, and we can replace flux by field current as done in above equations. DC motor control. Scheme showing armature voltage control and field current control by simple variable resistances. In actual practice, electronic converters such as mercury arc converters, thyristor converters or IGBT-based converters are used nowadays. DC motor control. We can see in the first graph that armature RPM rises with increasing armature voltage up to base speed, and then field current is reduced to increase speed to full speed. In the second graph we see that torque at nominal armature current is constant till base speed, and then torque reduces in proportion to field current. Kilowatt or HP increases with speed up to base speed as torque is constant, and HP rises with speed. But beyond base speed, since torque falls down, HP remains constant with increasing speed.